course, you all know that tendons are connective tissue consisting of mostly of ECM, in which type 1 collagen is the main component. Yes, other components are cells, fibrillar collagen, mostly type 3. Just a second, I have to get out of this thing here. There we go. Type 5, and of course, protoglycans. 60 to 90% of adult collagen, of adult tendon, sorry, is dry matter, is type 1 collagen. And this is the component that is mostly responsible for the tensile loading capacity. There is also a small amount of elastin, and it has probably a role in determining the elastic properties of the tendon. There is also an important component, another component, which is protoglycans, which constitute 0.5% of dry weight, made up of decorin and biclan. And this is important because it can retain large amounts of water. And also, one important feature about collagen fibers is that they form cross-linking, and these are collagen linking between collagen molecules, and have the effect of increasing the strength and the stability of collagen molecules. We also have a non-enzymatic cross-linking, mostly formed by advanced glycation end products. And these are probably the cause of the tendon dehydration. These play a major role in aging as well. Fibroblasts in adult tendon are elongated, and they are located in larger bundles of collagen fibers. And there are cellular processes that are spread between collagen fibers and provide contact to neighboring cells, which enables cell signaling. And of course, oops, sorry. There you go. As very eloquently introduced by Professor Kerr, the tendons are made up of collagen fibers, and these contain fibrils, which are made up by collagen molecules arranged in triple helixes. And one important feature of the collagen fibers is that at rest, they are crimped. In other words, they, as shown here, they are folded. And this is important because this crimping of collagen fibers is responsible for the toe region of the initial region of this stress-strain relationship of tendon. This is studied by placing a tendon in a Lindstrom instrument that stretches the tendon, and the deformation of the tendon is normalized for the resting length, for the initial length. So as you can see, when we initially stretch the tendon, we take up the slack of the collagen fiber due to the crimp, and then we enter the linear region. The linear region is where the tendon behaves elastically, and once in this region, the tendon collagen fibers are stretched, but they are not damaged. If we stretch a tendon below 4 to 5% of its length, then the collagen fibers start breaking up, and we go away from the linearity. And if we keep stretching the tendon, then the tendon fails, as shown here. What is important to note is that the stiffness of the tendon is directly proportional to the cross-sectional area of the tendon, and inversely proportional to the length. So if we double the cross-sectional area, the tendon stiffness increases by twice. And if double the length of the tendon, we halve the stiffness. So tendon stiffness depends also not only on its material properties, but on the dimensional properties, cross-sectional area and length. What happens to tendons with aging? has been very eloquently reviewed by the group of, again, of Michael Kerr, in this beautiful review by Swenson et al. And what is important to point out is that what we know, what at least has been described in the literature about the effect of aging and tendon, has been confused for many years with maturation. So there are very distinct changes with respect to what happens to the tendon when we, during the development phase, as opposed to what happens to the tendon during aging. So during the development phase, we can see that fibrous diameters increase, cellular density decreases as the extracellular matrix volume increases, and the matrix turnover decreases. The elastic modulus drastically increases during development, and also the crosslinks are drastically increased, and so does the cross-section area. But what happens with aging, the elastic modulus is more or less constant. It shows a small decrease. At least remember that these data are obtained in animal tendons. And what is also important to note that during aging, the crosslinks tend to slightly increase. And what is important to note also is that the amount of glycation drastically increases. The cross-section area of the tendon is mostly unaffected by aging. So does the fibril diameter, and so also the density and the matrix turnover also do not change much during aging. So these differences between development and aging are very important. The knowledge on human tendons, mechanics and structures is up to recent time were much less known. And this was due mainly to the fact that there were very few methods to study the tendon. We can study the tendon nowadays using ultrasound, at least to study its mechanical behavior. Here is a method that shows that by placing an ultrasound probe on the patella tendon, we can study the tendon extensibility during an isometric contraction, as shown here. You can see that the patella, the tendon at rest at 50% of the maximum force and at MVC, maximum voluntary contraction. You can see that as the contraction intensity progresses, the patella tip moves to the left as the tendon is stretched. So if we plot the tendon deformation against the tendon force, we obtain the classical tendon extensibility curve, and the slope of which is stiffness. Of course, tendons also shows not only an extensibility, but also it recovers when we release it from after being stretched. But what is important to note is that the tendon deformation upon stretching is not fully recovered during recoil. You can see that this curve does not overlap with the stretching curve. So that this means that the tendon shows hysteresis. And that the area of this curve, which shows the hysteresis, is actually energy which is dissipated during the recoil of the tendon, and is dissipated as heat. Also, there's an open question as to whether the aponeurosis or the free tendon stiffness is different. In this study by the group of Michael Kerr, it was shown that the stiffness of the aponeurosis was drastically lower than the stiffness of the tendon. There are other studies by the group of Fukunaga that shows equal or similar stiffnesses of the aponeurosis and tendon, and other studies that shows opposite effects. So it is still an open issue. But what is important to consider is that when we study the extensibility of tendons in vivo, inevitably we measure the extensibility not only of the tendon itself, but also is the result also of the extensibility of the aponeurosis. What happens to tendon in old age? In this study, we measure tendon elongation in young people, in middle-aged individuals, and older individuals. And this is the curve for the young people, this is the middle-aged, and this for the elderly individuals. You can see that for the same amount of force applied to the tendon, the elderly tendon, at least as we progress with aging, the tendon is stretched more and more. So the tendon becomes more extensible. And therefore, when we plot the stress-strain relationship, and we take a slope of these curves, the elderly tendon is less stiff than a young tendon. And this is also, we showed this in many studies, and this is a recent study that was performed by one of my ex-PhD students, Jonathan Quinlan in Nottingham, and we showed that comparing young and old people, there was a 31% lower tendon stiffness in older male individuals, and a 26% decrease in Young's modulus. So Young's modulus, I remind you, is the stiffness of the tendon, of the material properties itself, because its stiffness normalized for the dimensions. So it purely reflects changing in stiffness. What is important to note is that the tendon stiffness was correlated with the ability for rapid force development. And so in other words, the stiffer the tendon is, the quicker the ability to develop force isometrically. And these are probably important implication for the ability to recover from a fall during, when tripping over. So being able to maintain tendon stiffness is important as we age. And how do we achieve so? By training. With my ex-colleagues, Neil Reeves and Maganaris in 2003, we showed that if we train septuagenarians individuals for 14 weeks at 80% of the 1RM, we could really improve the tendon extensibility. You can see that this is the tendon extensibility before training, and this after these 14 weeks of training, and you can see that this curve is shifted to the left, indicating that for the same amount of force, the tendon after training is stretched much less. And so when we calculate the stiffness before and after training, you can see that after 14 weeks, there was a 64% increase in stiffness and a 69% increase in Young's modulus. So the elderly tendon retains a huge capacity to recover stiffness upon loading. So it is a very highly plastic tissue. And going back to the question of changes in tendon size, we actually, in young people, we demonstrated that in response to strength training, there is a significant increase in tendon size. This is not, it's a rather a modest increase. It's a 3% increase, which is on average, and which is larger in the distal regions of the tendon, as previously shown by the group of Michael Kerr that he just talked about this. And what was interesting to note was that the increasing tendon Young's modulus was mostly correlated with quadriceps physiological cross-section area as opposed to quadriceps force. So this suggests that this increase in tendon stiffness is not strictly, this increase in tendon cross-section area is not strictly related to the force itself, but is related to the history of training. Now, of course, when we consider tendon stiffness, we have
3 minutes left.
Okay, thank you. We have to consider that the tendon is in series with the contractile component. So we have to consider also the muscle responses to understand the impact on function. We found that when we train all the people, the fascicles with strength training, the length of the fascicles increased after 14 weeks of strength training. So this suggested, this was in the vastus lateralis muscles, this suggested that there was an additional sarcomere series. If it were for the changes in the fascicle itself, you can see that an increase in fascicle number would predict, upon contraction, a greater shortening of the sarcomeres. And this excessive shortening of the sarcomeres could have a negative repercussion on the length force relationship of the muscle, the ability to produce maximum force. But as we will see in a minute, this may be compensated by tendon changes. In fact, when we looked at the length force relationship of the fascicles before and after training, you can see that this was shifted to the right, indicating that because of a longer length, the muscle, the fascicles at a different optimal length. And if normalized for the resting length, you can see that they perfectly overlapping one another. And this was because as the individuals trained, tendon stiffness increased, as we saw before, and the increase in tendon stiffness tend to limit the amount of shortening of the fascicle themselves, enabling the fascicles to operate even after training in the same region of the length force relationship that we theoretically estimated from the Axley model. Lastly, and this is the last point, we recently trained individuals, elderly individuals, for a period of 8 weeks at 60% on the 1RM, either in a concentric fashion or eccentric fashion. What is important to note is that whether they train concentrically or eccentrically, the increase in muscle volume was the same, both in young and older individuals. This was the response of the young, this was the response of the elderly individuals. This was the delta, so you can see that the hypertrophy to concentric and eccentric training was very similar, both in the young and elderly. But what was important to note was that there was a progressive increase in tendon stiffness, both as a result of concentric training and eccentric training. And what is also very interesting to note is that after 8 weeks of training, the elderly individuals regained tendon stiffness to the same level of the young individuals. So you can see that here these values are very similar, both in response to concentric and eccentric training. Whereas there were no changes in tendon size throughout the 8 weeks of training. So to conclude, we can say that tendon fibril diameter, collagen content, and tendon size are mostly unaffected by aging, while cross-link due to glycation markedly increase. In vitro studies suggest that a decrease in the potential for human cell proliferation, as well as a decrease in the amount of stem and progenitor-like cells in the tendon. Tendon stiffness, material properties, that is to say Young's modulus and hysteresis, deteriorate with aging, whereas H tendon retains high adaptability to chronic loading, regaining stiffness comparable to that of a young tendon. And possible mechanisms for this are an increase in hydration due to reduced glycation and an increase in collagen synthesis. We've also seen that exercise improves tendon material properties, while changes in tendon size are more modest. To what extent tendon hypertrophy is the result of an increased collagen matrix or of an increased water content is yet to be established. Also, whether tendon hypertrophy is a physiological or pathophysiological response is clarifying, but I think in hearing Professor Kerr's reply to my question, it looks as if up to some extent, this is physiological. Maybe in marathon runners, perhaps, it does assume some pathophysiological aspects. In response to chronic loading, tendon is blind to the direction of contraction. It just sees the tension. So we are seeing that the adaptation to the tendon to eccentric and concentric loading is exactly the same. It just responds to tension. Lastly, muscle adaptation to resistive training seems compensated by those of the tendon. This seems to be highly advantageous for optimizing function. Thank you very much. And I'd like to also thank my collaborators and colleagues that contributed to these studies. Thank you.
Thank you so much, Professor Narici, for the kind presentation. Can I ask immediately one thing? Then I have seen that there are also many other questions. Sure. I have a doubt about the tendon that became less stiff with aging, but at the same time, in the clinical practice, we note that we became stiffer and stiffer with aging. So how we can compare the laboratory result and the clinical findings?
Yes, well, and it is true that there is an increase in collagen and content with aging, but and that we become, people are complain and to be stiffer, and also it is found clinically. But this doesn't actually mean that there is an improvement in tendon properties. There is a deterioration in collagen quality. The tendon material properties actually deteriorate. So what I'm saying is that an increase in collagen does not actually reflect an improvement in tendon function.
Okay, thank you so much.
You.
And Professor Feliciano, can have your question?
Yes, hi, Marco. Great presentation. You said something about you didn't find the difference in between eccentric and concentric contraction. Yes. You are talking about the tendon or the muscle fibers? No. The tendon. Because, you know, I was under the impression that for muscle mass, there is a great difference in growing of the muscle mass with the eccentric versus concentric. Do you think that your findings are because probably the extent of training, the amount of weeks you did, or the load was not enough, or you still think that there is no difference in between the two types of stimuli?
There is no difference between the two types of stimuli as far as the tendon is concerned. The tendon just sees the tension. It doesn't care the direction of the tension, as long as longitudinal, of course. Whereas for the muscle itself, instead, there is a huge difference. Of course, we know that eccentric training is a great stimulator of muscle growth. So the response of the muscle to the eccentric loading is, of course, greater than concentric loading when you use conventional training. Whereas the tendon, as I said, you know, it doesn't mind the direction.
Thank you.
Welcome.
There is another question, Professor.
Marco, hi Marco. It's very nice. Actually, we will, I guess, meet Friday for dinner then, just to not have to make an email.
Excellent.
Okay. But the question is the functional difference between aponeurosis and tendon. Could you just maybe speculate a little bit on it? Because basically we see the same material having so largely different properties. I realize you measured it in vivo. So can you speculate on that?
So, sorry, if I gather your question correctly, you say that in vivo we studied the myotendinous junction?
No, you showed a slide where you showed the different property of aponeurosis versus tendon in terms of the response to load.
Yes, yes.
I just wonder, it's the same material. Why is it so different?
Well, you see, when we talk about the extensibility, you have to take into account also the thickness of the tissue and the cross-section area. So that if you measure it in vivo, the fact that the aponeurosis is much less stiff than the tendon, this could give rise to differences in extensibility compared to the tendon itself.
So you think it's just the material properties, nothing to do that on the one hand, the muscles are attached on one side and the other side, whereas in an aponeurosis, they are attached all along the aponeurosis.
Well, it's a very long structure, of course, and so its length will also affect its extensibility. It also very much depends how you measure the extensibility of the aponeurosis. It's quite easy to measure the extensibility of the free tendon. That of the aponeurosis, there are different methods that have been used. And so that is why different labs report different extensibilities. So, it is an open issue. There is I cannot say whether they are the same or they are greater or less, because there are 3 labs reporting diametrically opposite results. But all I can say is that they may be different.
Let's discuss it on Friday.
Yes, of course.
Okay.
Okay, so I don't see other question. There are time eventually for another question.
I can, sorry, Carla, I can just kick in and say, you tried to put up a few suggestions, Marco, regarding the stiffness that occurs, the changes in stiffness occur relatively quickly. And you and others have tried to measure different things, and I saw your possibilities, but I mean, I'm as puzzled as you are, but maybe you could, where do you think the explanation is? Because it is rather pronounced changes in stiffness. I mean, with training. So what do you, I mean, deep in your heart, what do you think is the dominating factor, or do you think it's sort of a whole bunch of factors that play together? Because something must kick in that we can't see when we measure a lot of the things.
Yes. Well, thank you for the question. Thank you for the question. I think it's a series of factors. One, very important factor may be hydration. So basically training will reduce this dehydration effect that is associated with aging. The other effect could be, of course, and you've shown this, an increase in collagen synthesis, and there are plenty of studies that you showed that, or not plenty, but quite a few significant studies that show an increase in collagen synthesis. And we know, for instance, that fibroblasts produce in response to loading through the action of growth factors, they stimulate collagen synthesis. So this cannot be discarded. So I think it's an increase in collagen synthesis and hydration. Probably, at least this is my gut.
Yeah, but that's fine. I just wanted the speculation. Thanks very much.
Yes, welcome.
And Professor Angelini?
Yes, I have another question following up Protasi. Enjoyed your talk.
Thank you,
Marco, and I was surprised to see no difference in concentric versus eccentric tendon. So could you speculate on 2 things, What about the difference for muscle, and do you have any difference for denervated muscle?
Okay, so
I'm interested in ALS.
Yes. Well, let's start with the intact muscle and the intact tendon. The difference between concentric and eccentric loading is, as far as the tendon is concerned, there is no difference because the tendon only sees the tension. Whether it is in stretching or shortening, the tendon just sees the tension. So the response is the same. This is, of course, is not true for the muscle itself. The muscle will increase much more in response to eccentric training, simply because it is overloaded. And there are plenty of studies regarding this. As far as the innervated muscle is concerned, I'm not sure, because if you load a denervated muscle, the only way to make it contract, I suppose, is by stimulating electrically, artificially, of course. And in that case, you're stimulating the muscle itself, not the tendon. So you would get a muscle response, but not a tendinous response. So I don't think, I cannot recall any changes in tendon upon muscle stimulation, but maybe some study exists.